Alright guys, today I'm going to walk you through how to take the derivative of circular functions such as sine, cos, and tan. So this falls under Mathematical Methods, Units 3 and 4, Area of Study 3, Calculus. By the end of the video, I hope that you'll be able to calculate the derivative of circular functions, as well as understand the general graphical intuition behind what the derivatives are and why. Quick aside, why bother with derivatives? Again, they have a lot of real-world applications such as kinematics, which relate to, for example, the position, velocity, and acceleration of moving objects like cars, optimization problems such as minimizing cost functions, and growth rates, looking at how fast a company is growing. Quick overview. By now you should be pretty familiar with the derivative of polynomial functions like linear, quadratic, cubic, quartic terms. If not, here's a quick summary. If you have f of x equals x to the power of n, the derivative f dash of x is going to be n x n minus 1. So you grab the power, you throw it down front, and you decrease it by 1. I hope you're also familiar with the chain rule. So this is applied when you have composite functions like f of g of x. So if you want d dx of f of g of x, that's the same as the derivative of the outside f, and g of x stays inside, times the derivative of the inside function g of x. You might have seen it in this form where you have dy dx equals dy du times du dx. This is the exact same as this, it's just slightly different notation. In this case, u is just g of x, the inside function. So if these two things you're not too comfortable and not too familiar with them, please go through some of our previous videos and kind of get yourself up to speed before continuing with this one. So in this video, I'm going to introduce derivative of circular functions such as cos x, sin x, and tan x. And these questions can appear on paper 1 questions as a short answer response, or paper 2 questions as an extended response question as part of application-based questions. Okay, first bit of theory. The derivative of sine of x is cos of x. Okay, let's have a look at this graphically. So here is a basic sine graph, which has been restricted to 0 to 2 pi. Now, if you are familiar with this graph, you should know that this point here is 0, 0. This point here, corresponding to the maximum, is pi onto 1. This point here is pi 0, and this point here is 3 pi onto negative 1, and this point here is 2 pi 0. Now looking at these tangents I've drawn to these points, the derivative at these points is the same as the gradient of these tangents. If you're not too sure why, have a look through previous videos. Having a look at this point here first at 0, 0, we observe that the tangent to that point has a gradient of 1. So we expect that at x equals 1, the derivative will be 1. Okay? Next, at pi on 2, at the maximum point, we observe that the derivative is going to be 0 because the tangent is flat. Okay? So we expect that at pi on 2, the derivative is going to be 0. At pi over here, the derivative is going to be negative 1. Okay? So we've seen in the first section, you have a derivative of 1, and then you slowly decrease towards 0, and you start decreasing towards negative 1. So we're kind of seeing that here so far with the cos graph, right? And this point here corresponds to pi negative 1. After this, we observe that although it's negative, the gradient starts to increase towards 0, and it hits 0 at when x equals 3 pi on 2, because again the tangent is flat, which is the same as over here, shown over here. And then when you approach 2 pi, the gradient begins to increase, become positive, and approach a value of 1, which is shown here. So I hope that by looking at these tangents and the gradients of these tangents, you can kind of see why the derivative of sine x is just essentially cos x. Okay? Now, using the chain rule, which I've written here again, the derivative of sine g of x, which is a bit more of a general example, is the same as cos g of x times the derivative of g of x, which is g dash of x, so the derivative of the inside function. Okay, let's do some examples. So here is the same formula I just said, right? Where the derivative of sine g of x is cos g of x times g dash of x. Our first example is pretty straightforward. It's just the definition. F of x equals sine x, so the derivative is then cos x. Okay? Next example, f of x equals sine 5x. Well, in this example, g of x, the inside function, is 5x. So if I want the derivative of sine 5x, that's the same as cos of g of x, so cos of 5x, times the derivative of g of x, which is the derivative of 5x. The derivative of 5x is just 5, so you're left with 5 cos 5x. Okay? Next example. F of x equals sine x squared. In this case, g of x is x squared. So when we get the derivative of sine x squared, we get cos x squared, g of x, times g dash of x, which is the derivative of x squared, right? The derivative of x squared is just 2x, so we're left with 2x times cos x squared. Okay? Last example, if I have f of x equals sine x plus 1 squared, then the derivative, right, will be cos g of x, and in this case g of x is x plus 1 squared, so we have cos x plus 1 squared, times g dash of x, which is the derivative of x plus 1 squared. Okay? Now, derivative of x plus 1 squared actually requires us to use a chain rule. Okay? If you're not familiar, which I hope you should be, but here's a quick little refresher. We take this power, we throw it out front, we decrease it by 1, and we multiply the corresponding output by the derivative of this inside term, x plus 1, which is just 1. So we have 2 times x plus 1 to the power of 1 times 1, and then multiply by our original front term, cos x plus 1 squared. Okay? Bit of rearranging, we end up with 2x plus 1 times cos of x plus 1 squared. Okay, next bit of theory. The derivative of cos x is minus sine x. So similar to the previous bit of theory, but now there's a minus involved, okay? Let's have a look graphically. So the same type of tangent lines are drawn at these various points at x equals 0, x equals pi on 2, x equals pi, x equals 3 pi on 2, and x equals 2 pi. Okay? So, at x equals 0, the gradient is going to be 0 because the tangent is flat, which means that the derivative at that point is going to be 0, which is shown here. As we increase x towards x equals pi on 2, we observe that the gradient becomes increasingly negative and hits a gradient of -1 here, okay, which is shown here. As x equals pi on 2, the gradient becomes -1, so the derivative becomes -1. After this point, the gradient gets decreasingly negative, so still negative, but less and less negative as it approaches a derivative of 0, again because the gradient of this tangent is 0 at x equals pi, which is shown here. Then the derivative will start to increase as the gradient and the slope of the tangent increases to a value of 1 when x equals 3 pi on 2, which is shown here. And then as x approaches 2 pi, the derivative begins to flatten out back towards 0 and hit 0 back at 2 pi, which is shown here. So you can see that cos x, the derivative is actually sine x, but reflected over the x-axis, so minus sine x. Okay? Cool. So using the chain rule again, a more general case where we have cos of g of x, the derivative of this whole thing is actually minus sine g of x times g dash of x. Okay? Let's do a couple of examples. If I have d dx of cos g of x, the derivative of cos g of x, this is minus sine g of x, g dash of x, which I just outlined in the previous slide. That's rewritten here. Example 1, f of x equals cos x. This is by definition, the derivative is just minus sine x. Okay? Nothing too special there. Example 2, f of x equals cos 5x. So in this case, similar to before, g of x is 5x. So we use this formula, we're left with negative sine 5x times the derivative of 5x, which is just 5. Okay? Cos x squared, again similar to the previous gets with sine, the g of x term here is just x squared. So the derivative is going to be minus sine x squared times the derivative of x squared, which is 2x. So we're left with minus 2x sine x squared. Okay? Final example, again, similar sine case. In this case, g of x is x plus 1 squared, right? So if we want the derivative of cos of x plus 1 squared, we have minus sine x plus 1 squared times the derivative of x plus 1 squared. And just as we did before, right, we grab this power, we throw it out front and decrease it by 1, and times the corresponding thing by the derivative of the inside, which is just 1. So we're left with minus sine x plus 1 squared times 2 times x plus 1 times 1, which is just minus 2 times x plus 1 in brackets times sine x plus 1 squared. Okay, final bit of theory. The derivative of tan x is 1 divided by cos squared x, or sec squared x. Now, I don't think you cover sec graphs and methods, so you don't have to be too worried about what this is, as long as you know that if you see this notation, is just the same as 1 divided by cos. Okay, so sec squared in this case is 1 divided by cos squared. Okay, so graphically, this is a tan graph, right, just for one period. We observe that at small x values, we have a very, very steep gradient, so a very, very large derivative. As x approaches 0, it's still positive, but it kind of flattens out a little bit, yeah, towards, let's say, a value of 1, derivative of 1. And then after that, you start to increase back again, just like you were over here. So we see we're going to expect a bit of symmetry between this side and this side of the graph when it comes to the derivative, which is exactly what we observe here, right? We have a very large derivative value. It decreases towards 1 as x equals 0, and then increases back again in a symmetric fashion. And this is the graph of sec squared, or 1 divided by cos squared x. Okay? Using the chain rule again, the derivative of tan of g of x, more generally, can be written as g dash of x divided by cos squared g of x. Okay? Few examples. Here's that formula again. If f of x equals tan x, we'll know by definition that the derivative has to be 1 on cos squared x. If we have f of x equals tan 5x, then the derivative is going to be g dash of x. In this case, g of x is 5x, so we have the derivative, which is 5 divided by cos squared of 5x, which is just g of x. Okay? Next example, f of x equals tan x squared, so like in the previous case, so this is now g of x, which is x squared. The derivative is going to be g dash of x, so the derivative of x squared, divided by cos squared of x squared. And the derivative of x squared is just 2x, so we're left with 2x divided by cos squared x squared. Last example, f of x equals tan x plus 1 squared. Now the derivative of this, in this case we have g of x equals x plus 1 squared, like we did previously with the sine and cos cases. The derivative of this is going to be g dash of x, so the derivative of x plus 1 squared, divided by cos squared x plus 1 squared, which is shown here. And again, the derivative of this can be taken using the chain rule. So you grab this power, you throw it out front, you decrease it by 1, and you times the output by the corresponding derivative of the inside term x plus 1, which is just 1. So we're left with, finally, after a bit of simplification, we have 2 times x plus 1 in brackets divided by cos squared x plus 1 squared. Okay, final tips. Just like in the case of the previous video where we talked about exponential and logarithmic functions, practice is super important. Okay, if you're having trouble using the chain rule, it'd be maybe worthwhile to define what g of x is. So for example, in this case, g of x equals x squared, and writing down what g dash of x is separately if it helps out. Don't skip steps until you're comfortable with how you're doing the question and you know that you understand the content pretty well. If you're having trouble, don't stress too much. It's okay. Sometimes it takes a little bit more time to learn the content than usual. Just spend some time practicing, and I'm sure it'll all come to you in due time. All right. Thanks, guys.